Buenos días. Gracias, thank you to the organization to allow me to be here for this talk, and to all of you to be here also. Today, I will talk about the deep near-infrared view of the Ophiuchus galaxy cluster. This work is part of the PhD thesis of Daniela Galdeano, and we made this work in collaboration with astronomers from Chile and also from Cordoba. So many of them are present today, and if you have questions, you can also ask them for the for the question. We are very happy because this work was accepted for publication the last week, so it will be available on archive very soon. Let's start with a brief review of the Ophiuchus galaxy cluster. It is the second brightest galaxy cluster in the X-ray sky after Perseus. So it is a very hot, really hot galaxy cluster with a central cool core. It has a CD central galaxy that has been catalogued for two mass extended source catalog. And this galaxy cluster has been mostly studied in X-rays. We will know the reason. One of the main results in X-ray is the small difference between the position of this CD galaxy and the X-ray peak. That could be due to the presence of mergers, merger with the very close galaxy clusters. There are some discussion about this topic, but at least we have some clues about that. So the reason, because it is mostly studied on X-rays and not in other wavelengths, are the position on the sky. It is located on the Zone of Avoidance, which is at low latitudes behind the Milky Way at the edge of the bulge, where you can see here the position of Ophiuchus, which is just above the galactic center, where the big amount of stars and gas hampers the optical observations. So perform studies in optical observation really is a huge challenge. However, some few works in opticals have been done. For example, derived et al. In 2015 performed an optical studies of the dynamical properties of 142 galaxy cluster members. They took a sample of galaxies in different wavelengths and performed the spectroscopy of these galaxies and estimate the redshift of the galaxy cluster around 0.03. They also estimate the velocity dispersion, which is similar to that estimated with X-ray data, and the mass, which is more than 1 to 10 to 15, 1 per 10 to 15 solar mass, which is even higher than the mass of the estimated mass for the coma cluster. So this is a really big and potential galaxy cluster that definitely need to be very well studied. In addition, derived also studied derived the galaxy luminosity function, estimating that there are an excess of bright galaxies compared with the coma galaxy clusters. And of course, the most of the galaxies used for this work were already catalogued for 2 mass. Fortunately, we are very lucky because we have the extended version of the BBX Survey, which cover a big portion of the sky, around 1,700 square degrees, divided in 1,028 individual tiles. Each tile has an area of 1.5 square degrees, and the observations are performed in J, H, and KS bands. Just for a reference, the red area is the original BBX survey, and the other colors correspond to different parts of the extended version of this survey, which is VVVX survey. Well, here we could observe the first time this beautiful galaxy cluster for a RGB image. We also have some experience working with BBB data on the region of the bulge. For example, in 2014, we found the near-infrared counterpart of an X-ray galaxy cluster. Well, we could make some analysis of the central part of the galaxy cluster, and more recently, we also found a new galaxy concentration behind the Milky Way, where we could find more than 600 galaxies in a very few regions of the sky. Now, in this moment, we are trying to publish the result of the spectroscopic observation of some of these sources. And well, we definitely found a new galaxy cluster in this region. So with all this information, we were very happy, but not so happy because a small detail is that the CD galaxy of the Ophiuchus galaxy cluster is located at 10 arc-minutes of the survey edge. So we only can map completely the central part of the Ophiuchus galaxy cluster. But at least it's a good news. And it is located in the tile B506. In addition, to the central part, we map the half or the 60% of the external region of the Ophiuchus cluster up to 2 megaparsecs, just to have the most complete view of the galaxy cluster. We follow the recipes from the Galdeano et al. Paper just to obtain the galaxies and to select the galaxy candidate, obtain the sources. We download the image from the VISTA Science archive, and we run extractor. We select the parameters to separate the stars from the galaxies. We use the same conditions to select the galaxy candidates, and in addition, we also perform the visual inspection. We cannot avoid the visual inspection. It's very necessary to clean the sample, and in this visual inspection, we also classify the object by the morphological features. So the final catalog contains 537 galaxy candidate members of the Ophiuchus galaxy cluster. For the moment, and candidate members we will know in the future with spectroscopic confirmation. Okay, this is an schematic view of both tiles. We need to add a new tile to complete the full analysis of the galaxy cluster. Here in the center, you can see the CD galaxy with the cyan dots. There is a dashed magenta line with covers their central regions with a radius of 360 kiloparsecs, and the 2 megaparsecs are delimited by the solid magenta line. So you can see the red dots are those galaxies classified as ellipticals, the blue ones as spirals, and the green ones are uncertain galaxies because they didn't have enough enough features to be classified as elliptical or spiral. And these galaxies are in general galaxies with very low brightness surface.
3 minutes. 3 minutes.
3 minutes, okay. Here you can see the examples of the 3 types of morphological classification. These contours are from X-ray taken from ASCA. One of the results was the morphological density diagram, where the red line corresponds to the elliptical galaxies, the blue one to the spirals, and the green one to the uncertain galaxies. So you can see that this behavior is as we can expect from a galaxy cluster, and we divide the regions to the inner region, which is completely studied, and the outer region between 360 kiloparsecs and 2 megaparsecs, where we can study only the half, and we calculate the amount of galaxy in one of these regions, and for every morphological types, and also we compare the total with the existing works from direct and also from 2MASS, and we can see that we have at least 4 more times galaxies in the inner region and 8 more times galaxies in the outer region. Of course, we are comparing exactly the same area. In addition, we calculate the red sequence for the inner region, where we can see a very nice red sequence in the infrared color magnitude diagram, and estimate the red sequence slope, which and the value is in agreement with that expected for the cluster, for the redshift cluster. Here we can see discriminated the galaxies by the morphology and also by the catalogs. And we also compare our result with the observational and simulated result. These are the density profile. This is the solid line is our work. The dashed line is the work from direct, which is the most complete work up to the moment in optical wavelength. This gray area is the density profile if we take only the galaxies within the red sequence, and this point here is this triangle is that corresponding to the simulated data. We built a mock catalog from the L galaxy semi-analytic model and count the galaxies in a region, in an overdense region, estimating that we should find in a mock catalog reproducing the BBB catalog around 432 galaxies per megaparsec square. So from these results, we have 3 main conclusions. One of them is that we found 537 galaxy cluster candidates with need, of course, spectroscopic confirmation. All of the direct galaxies are included in this sample, but we increased the sample of galaxies 7 times with respect to the number reported in previous work. Our investigation of this hidden population of the Ophiuchus galaxy clusters underscores the importance of these clusters as a prime target for the future photometric and spectroscopic studies. And again, the result of this work highlights the potential of the VVVX survey to study the extragalactic source in the zone of avoidance. That's all. Thank you very much.
Thank you. So we have time for 2 questions.
Sure. The Dressler relation, the Dressler plot that you showed, the number density of galaxies. So the spiral galaxies shouldn't go upwards outside the cluster. Maybe
Yes.
those greens are.
Yes, we can expect that. But it is probably that most of these spiral galaxies, which are weaker than the elliptical ones, are included here. But really, we could not classify them as spiral. So it could be a mixture of elliptical and probably the most of them are spiral. But they're really clear because to be classified as spiral, they have by A's, they have to be edge off with this kind of morphology features of disk, because if they are face on, we don't have enough resolution to observe the disk and everything. Yes, yes,
Yeah.
edge on,
Yeah,
edge,
maybe.
yes, thank you.
Thank
Yeah.
Nelson.
Thank you, Georgina. So I was wondering, how bad is extinction in this region of the sky?
Sorry?
How bad?
Oh, the extinction, yes. Well, the extinction in this, yes, is around 1 magnitude in optical wavelengths. It's not the worst part of the survey, but anyway, is great. It is big enough to avoid to observe many galaxies in these regions.
And just one last question. So the morphology, you obtain the morphology of your galaxies from BBX, from the infrared?
Yes.
Okay.
Yes. Oh, yes, but from the image, yes. O sea,
From the images.
From the
no
image.
Data. We see RGB images and
Yes,
and
yes,
that's
from the
fine.
image.
Yes, we will.
It is important to mention that BBB is 3 magnitudes deeper
Yeah.
than 2 mass.
I want to say that. Yes.
So we could observe many more galaxies than that already existing. And yes, the morphology is by our visual inspection from this image from BBVX.
Yes, with this magnitude coverage deeper than 2 mass, we go through the galaxy at these extinction levels.
Yes, we can reach magnitudes to KS around 16.5, because after that magnitude, our eyes cannot distinguish anything.
Okay, great. Thank you very much.